Hello friends, today we are going to discuss a data structure which is very important in many of the problems. It is called heap, and you can also see that I am showing you some of the important problems which can be solved using heap. Most of them are like finding top k frequent words, finding top k frequent elements, kth largest element, or the k largest elements, and kth smallest element. So there are many problems which can be solved using heap. We need to understand few basic concepts of heap. You don't need to memorize them. Once you understand them few concepts, then you have to practice some problem, then you will be able to use them in other problems. So without wasting further time, let me go through the basic properties of the heap. So heap can be represented or can be called as binary heaps because they have one left and one right child. It's basically a binary tree with the properties that the current node wherever we are or parent node will always be smaller than its both left and right child. It will be called min heap. And if parent is greater than its left and right childs, so for example root is 5 and left child is 1 and right child is 2, so this will be called as max heap. And the second thing to know that it's almost complete binary tree. It means it is filled from left to right, and it will always be complete or full until maybe in the last level. So we are not sure whether last level will be full or not, but we are sure that all the previous levels will be full. And because of this property where we are inserting each element one by one in a proper complete tree manner, complete binary tree manner, so it can be heap can be basically binary heaps can be represented using an array. So the top root is like 0th index, then the left child this is at 1 index, this right child is at this index 2 index, and same way. And to find out, for example, if you are in array, you cannot visually see how your heap looks like, so you have some formulas to find out what is the parent of that element and what are the two left and right childs of that element. So for example, if I am at index 3, so I can use this formula to find the parent. So n minus 1 by 2, 3 minus 1 by 2, 2 by 2, 1. So it means the first index, so here in array first index has value 2, so it means that the parent of value 4 is 2. And if I want to find out what is the left and right child of an index, for example, let me find out the left child of this value 2, which is at index 1. So left child can be find out by 2n plus 1, so 2 into 1 plus 1, so that is 3. So third index, it means 4 is the left child of 2, and 2n plus 2, it means fourth index, so 5 is the right child of the 2. So this way it can be represented as an array, and you can easily find out what is the parent and what is the children of a particular node using this formula. Again, to find out parent, it's n minus 1 by 2. N is the index where you are currently trying to find out the parent of, and 2n plus 1 for left child and 2n plus 2 for the right child. Okay, so now let's see what operations are normally performed in the heap. So there are majorly two operations, which is called extract min and insert in the heap. Extract min is order of log n. If you just want to check the minimum element in min heap, it's order of 1. So it doesn't take any time to find out what is the min element because it's always the root element. So if you just want to peek at the minimum element, then it will be just order of 1. But if you are extracting min element, it means you are removing this one out of here. Then we have to perform operations to make this min heap again. So for example, the algorithm is whenever you extract a minimum, it means you take the root value out. So you simply copy the last value, which is 6, to this root element, and you delete this link here. And after this, we call it as a heapify operation. So we will make sure that property of the heap is met. So for example, this is min heap, so our root element should always be lesser than the left and right child. So we compare basically this parent element and the value of this left child. So 6 is greater than 2, so we can simply swap it with the 6. So now 2 will come here and 6 will come here, And one thing to notice, you know, no need to find out which of these left or right child is the minimum one to swap with, because the order doesn't matter in this case. So the only property it matters, that root should always be minimum than left and right child, but the order of left and right child doesn't matter. Okay, so here, because left child, we compared the value of the root element with the left child, and left child was basically lesser than the root element, so we just swapped it. So now root has 2 and we have 6 in the left child. Same way we will check here. Okay, is 6 lesser than the 4 element? No, so it means it is not satisfying the min heap property, so we'll simply swap it with its left child. So we will have 4 here and 6 here, and now we are done. So if you see, like at each heapify operation, we are going past one level, which is basically will make it as an operation of order of log n. So this is extract minimum, and we already noticed that just to check what is the minimum value, it will just order of 1. Then if you want to insert any element, so for example, let us say that we want to insert one element 7. So we basically insert it at the end, and then we will try to check the heapify property and see whether it's in proper place or not. So we check this 7 is less than 2, and so it is not breaking the heap property, so it is at a right place. Let me take one other example. So for example, let's think. Okay, so I have created here one other example. So root is 10, then left child 15, right child 20, and then there is two more elements, 25 and 90. So for example, now I want to insert one value 5. So I will just put it at the end. So I will insert it here. Then I will check whether this break heap property. So we are having min heap. So we need to make sure the parent of this newly added node is lesser than this value. But here we can clearly see 20 is greater than 5. So it means we'll simply swap 5 with 20. So now it will have 5 and 20 here. Same way we will again check the parent and its value. So parent is still greater, so 10 is greater than 5. So it means I have to swap 5 here and 10 here. So final tree will become 5, 15, 10, 25, 90 and 20. So this way we can insert and extract min. So you need to remember the runtime for extract min is order of log. If you want to insert, it's order of log n. So these are the properties of heap. Now with that, let me solve one problem. So it will give you an idea how heap can be used. So for now I am taking one problem which is very common. So let's go to that problem. Okay, so we will solve this problem. This is an easy problem from Leetcode 1046, last stone weight. And the problem is like we are given a collection of stones and each stone has a positive integer weight. So for example, we have this integer array 274181. So basically these are the weights of the stone, and each turn we choose the two heaviest stones. So we take two heaviest stone from the array and smash them together. Suppose the stones have weight x and y with x less than equal to y. The result of this smash is x. If x equals to y, both stones are totally destroyed, and if x not equal to y, the stone of weight x is totally destroyed, and then the stone of weight y has new weight y minus x. So what it means, for example, we have an input array here. So we have to take first two largest elements, so 7 and 8, and we have to compare their values. In case they are same, so it will become 0, and then both will be destroyed. But in case they are not equal, we have to take the absolute difference of those two values. So in this case 8 minus 7 or 7 minus 8, which is basically minus 1 or 1, and we will take the absolute value that is 1, and we will again store that 1 inside the array. And after that we will take the next two largest value, which will be basically 2 and 4, and we will smash them together, and it will so the result will be 4 minus 2, that is 2, and we will again insert 2 here, and these are 3 ones. Again we will take two largest, so 2 and any one of these ones, so 2 1, so remaining will be 2 minus 1, so we will insert 1, and already 2 ones were there, so they will come here. Again we will take top 2, so 1 1, so they are equal, so they will be destroyed, then there will be only 1 left, and we have to return that value. In case nothing is left, so just we have to return 0. Okay, to solve this problem, as we know, we have to take at every step two largest elements. So we will create a max heap. So in Java we use priority queue, and it is priority queue of integer. We'll call it as max heap equals new priority queue. And because we are going to create a max heap, we need to define the comparison operator. So it will be, if we are inserting a and b, we need to insert whichever is higher or larger. So we will use b minus a. Okay, now we'll store each stone from this stones array one by one into heaps. So for int I is equal to 0, I less than stones dot length I plus plus, and max heap dot add stones of I. Okay, so now we have a max heap ready, and for now at the top there will be element 8, and we have to take the top 2 element, right? And we have to run this algorithm until we have at least one element over there. Okay, so we can now run a loop while max heap dot size. So size is basically will give you the number of elements in the heap is greater than 1. Why we are doing greater than 1? Because if we max heap size is 1, we can simply return its value, and that will be the final answer. Okay, so we need 2 element from the top. So we will say int stone1 is equal to max heap dot poll. So we'll take the largest element out. So once this step is done, automatically this heap will be reorganized, and 7 will be the now the root element. So again we'll do int stone2 is equal to max heap dot poll. Okay, so now we have 8 and 7, and we just need to take their absolute value, and if it is 0, we need to remove it. If it is not 0, we have to insert the absolute value in the heap again. Okay, so if stone1 equals stone2, so we no need to do anything. So we'll just check if stone1 is not equal to stone2. So simply we will insert in the max heap dot add, and what do we insert? We insert the absolute value. So math dot abs of stone1 minus stone2. Okay, so what we are doing here, we are subtracting one stone from another stone. So it may come as I think it will always come as positive value only, but it's all right. You can do an absolute function so that we are never inserting a negative integer over there. So now once it is done, this loop will keep on iterating until we have only one element left. So there is a while condition override. So at the end we can just simply return the max heap dot poll. And one thing to notice, it may happen that we don't have any element over there. So for example, in the last condition we only had 2 values, so it will go inside this, and those 2 values might be equal. So for example, stone1 is equal to stone2. In that case we are not inserting anything in this heap again, so heap size will be 0, or heap won't have anything. So we can just simply check again, if max heap dot size equals 0, then we can just return 0, and if it is not the case, we can return max heap dot poll. Okay, so this way this program will run fine. So let's try to run this code. Okay, so and we can submit this code, and this is accepted. Okay, that's it friends. That's all for today, and this, I hope this helps you, and whatever 3 problems I have done, you can revise them, and you will be amazed to see how many problems could be solved using heap. Let's see the runtime complexity of this problem. So it's a heap. We are running this for complete stones length. So it will be, if the number of element in the stones is n, so it's n log n. And here we are just extracting some value, so they are always log n, so it won't be contributing in order because already we have order of n log n. Yeah, that's it. So runtime complexity is order of n log n, and space complexity, because we are using a max heap and we are storing all the stones over there, so it will be order of n, where n is the size of the stones array. That's it, friends. I hope you enjoyed this video. Please like or subscribe. Thank you.